Today we expose a hidden enemy inside blast furnaces, that is alumina, and we know its impact is enormous. This compound silently accumulate from multiple raw material affecting furnace efficiency and cost of production immensely. Understanding its sources and impact which help us build to optimize operation and prevent productivity losses. Now, as you can see, the sources of alumina in blast furnaces, alumina mainly comes from four sources. Iron ore contributes from about 70% of total alumina load because it contains gangue minerals. These vary widely based on core sources and blending. Metallurgical coke adds roughly 20% through its ash content, which contain alumina. Ash level matter here. Pulverized coal injection contribute another 8% increasing with higher injection rate, often overlooked. Fluxes like limestone add around 2%. Though small flux alumina still require attention if problem persist. Now, coming to our next slide, which is about the impact of alumina on furnace performance. High alumina content causes significant operational issues like inefficient heat transfer and decreased furnace permeability, reduce overall efficiency. It increases the energy consumption and can cause thermal stress to furnace lining. Also, the resulting condition destabilize the operation, leading to higher fuel rates and lower production. Now, coming to the detrimental effect of the alumina on slag, uh, and we know that slag alumina changes slag chemistry adversely. It raises the liquidus temperature, making slag less fluid and harder to handle. Reduced slag viscosity hinders sulfur removal, also impairing desulfurization. It increases slag viscosity, obstructing slag flow and gas permeability. Now, poor slag properties and furnace health. These negative changes in the slag alter furnace operation, where permeability is drastically reduced and increased pressure drop cause unstable furnace condition. This result in lower production rate and increased coke consumption due to inefficient heat transfer. Higher silicon content also favor unwanted silicon reduction, further complicating the control. Alumina monitoring and optimization, which is supposed to be one of the very important aspect. Controlling alumina require systematic monitoring, like analyze raw material and slag chemistry consistently. Use data driven insight from hot metal and processes. Monitoring to adjust burden and fluxes. Optimize burden distribution, furnace temperature and slag properties, which all improves efficiency and reduce alumina impact. So we can say that timely analysis of the inputs is must, and wherever the impact is huge, corrective measure is to be taken on a right time. Otherwise, the effect to revive the cost of revival of the furnace towards normalcy will time consuming as well as cost consuming. So hence, whenever we come across a signal symptom, accordingly corrective action taken without much delay. And this is what is we have already talked about the monitoring part, and this is how we have to optimize the furnace operation, in which we must have to look into slag chemistry, its temperature control, burden distribution, and slag modification, because overall evacuation is also a topmost agenda.